Welcome to this online lecture series in organic chemistry. In this video, we are going to discuss methylene insertion method for the preparation of organometallic compounds. Now, in this method, actually metal or non-metal halides, when treated with diazomethane, that is CH2N2, then methylene insertion takes place in metal halide or halogen bond. Actually, metal or non-metal halides such as silicon tetrachloride, germanium tetrachloride, mercury dichloride, when treated with diazomethane under suitable conditions, methylene gets inserted in between metal or element halogen bond, for example silicon chlorine bond, and there is a formation of organometallic compound. Very easy method. We'll take example. Suppose there is a silicon tetrachloride. When it is treated with methylene or diazomethane, then in between one silicon and chloride bond, methylene insertion takes place and we get CiCl3 CH2Cl. So 3 silicon halogen bond remains as it is, but in between one silicon and halogen, that is chlorine, there is a insertion of methylene and we get organometallic compound. There is a formation of carbon silicon bond. Another example, when germanium tetrachloride is treated with diazomethane in presence of copper catalyst, we get organometallic compound. Again, there is an insertion of methylene between germanium and chlorine. At the same time, there is an evolution of nitrogen. Similarly, when mercury chloride is treated with diazomethane, then in first step, in between mercury and halogen bond, there is an insertion of methylene. At the same time, nitrogen gas is evolved. There is an insertion of another methylene group between remaining mercury and halogen bond. So it reacts with diazomethane, another diazomethane molecule, and in between both the mercury and halogen bond, there is an insertion of methylene. So in this way, this is the organometallic compound. So in this methylene insertion reaction, this is also called as methylation reaction. Metal or non-metal halide like silicon halide or germanium mercury halide, when treated with diazomethane, then we get organometallic compound. Then another example is when tin halide. So when tin is attached to 2 halogen atoms and 2 methyl groups, then when it is treated with diazomethane, there is an insertion of methylene group between one of the tin halogen bond and we get organometallic compound. Now next part is chemical reactions of organometallic compounds. Chemical properties or chemical reactions of organometallic compounds. The chemical reactivity of organometallic compound varies or changes widely from one compound to other compound, because the activity of organometallic compound, it is correlated with Carbanion character of organic group. There is one organic group attached to metal, and that organic group acts as a carbanion, and depending upon the activity of that carbanion, the reactivity of organometallic compound changes from one compound to other compound. Again, activity of organometallic compound depends upon difference in electronegativity between metal carbon bond and availability of the coordination site on the metal atom. So coordination number of metal, it can be extended, and this is also useful for its chemical reactivity. Okay, so we are going to discuss the first reactivity of organometallic compound, that is reaction with oxygen and halogens. Organometallic compounds of electropositive elements are good reducing agents, and their reducing characters increases with increase in electropositive nature of element. And organometallics of electropositive elements containing vacant orbitals, these are pyrophobic. Pyrophobic means what? They spontaneously ignite in contact with air and cause explosion. This is called as pyrophobic. For example, tetramethyl lithium, when ignited in air, spontaneously reaction occurs, oxidation reaction occurs, and there may be possibility of explosion. This nature is called as pyrophobic nature. Now reactions of organometallics with oxygen, these are highly exothermic. Heat is evolved during these reactions. For example, when organometallic compound, this M is arsenic and antimony, especially the trialkyls of group 15 or dialkyls of group 16, these are oxidized to suitable oxides even with the limited supply of oxygen, retaining their metal carbon bonds. Metal carbon bond remain as it is, only there is a attachment of oxygen. So oxidation number of this M, it can be extended. So when this trialkyl arsenic or trialkyl bismuth antimony, when treated with limited supply of oxygen, there is a reaction between organometallic compound and oxygen. There is oxidation of this compound. Reaction is exothermic. Similarly, when dialkyl selenium or dialkyl tellurium, here is selenium or tellurium, reacts with limited supply of oxygen, again the selenium alkyl group bond remains intact, there is no change, but oxygen is attached to the element, that is selenium or tellurium. So this is about the reaction with oxygen. Now next part is decomposition of organometallics by halogens. Now halogens decompose organometallics and form hydrocarbon halides or alkyl halides. For example, when ethyl lithium treated with bromine, so there is a replacement of this lithium by bromine and we get ethyl bromide, and there is a formation of lithium bromide. In this way, organometallic compound is decomposed. Then cleavage of metal carbon bond takes place. Halogens generally cleave or break metal carbon bond in organometallic compounds, and the ease of this cleavage reaction depends upon electropositive character of element or metal. For example, when alkyl lithium is treated with halogen, that is X2, then there is a replacement of this alkyl group by halogen, we get LiX and Rx. Similarly, trialkyl aluminium, when treated with halogen, there is a breaking of metal carbon bond and we get aluminium trihalide, and at the same time there is a formation of alkyl halide. Similarly, trialkyl boron, when treated with iodine, there is a breaking of alkyl boron bond, and these are replaced by alkyl boron bond is broken, and one of the alkyl group is replaced by iodide. At the same time, there is a formation of alkyl halide. Similarly, when trialkyl gallium is treated with halogen, one of the alkyl and gallium bond breaks and alkyl group is replaced by halogen. So in this way, halogens are able to break metal carbon bond, and there is a decomposition of organometallic compound. Now, chlorine and bromine reacts with tetraalkyls of group 14. For example, tetramethyl silicon, when treated with chlorine, there is a formation of, or one of the bond between silicon and methyl group breaks, and methyl group joins with one of the chlorine, and there is a formation of methyl chloride. Okay, and methyl group, it is replaced by halogen. Similarly, when tetramethyl gallium is treated with bromine, and when mixture is refluxed for 24 hours, then one of the methyl group is replaced by bromine, and that methyl group joins with bromide, and there is a formation of methyl bromide. Similarly, tetramethyltene, when treated with chlorine, and in this reaction again one of the methyl group of organometallic compound, it is replaced by chlorine, and that replaced methyl group joins with chlorine, and we get methyl chloride. The next part is oxidative addition with halogens. So here especially chlorine and bromine reacts with tetraalkyls of group 14. For example, the especially tetraalkyls of group 14 means when it reacts with tetramethyl silicon. When chlorine reacts with tetramethyl silicon, there is a formation of, or there is a breaking of silicon methylene methyl group bond, and we get methyl chloride. Reaction is already discussed. Now next part is oxidative addition with halogens. Now here trialkyls of phosphorus, arsenic, antimony, trialkyls of phosphorus, arsenic, antimony, when reacts with halogen, then there is a actually reaction with halogen, and these two halogens directly attached to metal, and oxidation number, or sorry, coordination number of metal gets expanded. So Mr3 plus X2 gives Mr3X2. Oxidation number of metal is extended, and there is oxidative addition of halogen takes place. Similarly, when dialkyl selenium or tellurium reacts with halogen, again the bond between selenium and alkyl remains intact, but two halogen atoms are attached to selenium or tellurium. There is a expansion of coordination number of selenium or tellurium. So this is what is oxidative addition with halogens. So in this way, the oxidative addition takes place